right, so I'm going to skip over this cylindrical can question. We're definitely going to do this one, but I'm going to skip over it for a hot second. Something happened bizarre here. This question is meant to take up this page, so it looks like you have a whole blank page, but that was supposed to be the headliner there. And I'm going to actually jump to this question. Find two numbers whose difference is 100 and whose product is a minimum. You have a couple of these on your homework, all right? It's a nice question. So find two numbers whose difference is 100 and whose product is a minimum. Product means multiplication. Okay? So we're minimizing their product, right? That is the thing that we're going to take the derivative of, their product. And we've got to pick two numbers, all right? We're going to say that they're two different numbers, all right? So we're going to say x is number, I don't want to say number one, but number, if we want to call it number A, and we'll call number B y, all right? Those will be the two numbers that I'm talking about. So they tell me that these two numbers, their difference is 100. So when I subtract them, their difference is 100. X minus y is equal to 100. And they're telling me that their product is a minimum, all right? So I'm just going to use P for product is equal to x times y, and that's what I'm going to minimize, all right? Minimizing that product, all right? So this is very similar to the problem that we just did, where we have an expression in terms of two variables we need to take the derivative of. We have another expression that I can rewrite pretty easily. So I'm going to rewrite the difference expression and plug it into the product because the product is the thing I'm trying to minimize. This is what I'm working with. So I don't care which variable you solve for. It really doesn't matter. I tend to solve for y and plug in. So I'm going to say y is equal to, if I add y over and subtract 100, y is equal to x minus 100. All right, and I'm going to plug that guy into my product. Once again, I'm trying to minimize my product. That's the thing I'm taking the derivative of. That's why I'm not plugging it in vice versa. This is the thing I really want to work with. So if I plug in, x minus 100 for y, p equals x times x minus 100, you could do a product rule and take the derivative here, or you could distribute, make your life a little bit easier. All right. I'm going to take the derivative of this. 100x. Take the derivative of this. P prime. We'll have 2x minus 100. Same thing that we just did. Set the derivative equal to 0. I'm going to have 2x is equal to 100. X is equal to 50. Okay, this is our only option, all right? So I know it's really like tempting to just be like, oh yeah, this is the minimum. This is the thing that's going to give us our minimum. Don't do it, okay? Don't do it. Make sure that you get a minimum first and then go finish this problem, right? Make sure that you get your minimum. All right, now I have no restriction on these numbers. Our numbers can be anything that they want. There's no domain issues or anything like that. So I'm just going to create my mini table. And this is just to make sure that I did get a minimum, right? This is to make sure that this number is a minimum value. Negative infinity to 50. Big range. Pick 0, right? And then 50 to infinity, you can pick whatever number you want. 51 works for me. Now, if I plug in 0 into the derivative, I'm going to have 2 times 0 minus 100. This is going to be negative. And if I plug in 51, 2 times 51 is going to be 102. But 2 times 51 minus 100, that's going to be a positive number. And if you like to, like I said, if you like to label this out just so that you get in that habit, that is definitely not a bad thing, right? We want to make sure that we know these kind of little, what these rows stand for. So what this is telling me is that this thing decreases, it reaches 50, and that it increases again. So 50 is a minimum, all right? Minimum. Check. Works out great, right? So that's what we want. So all, like, now that I've confirmed that it is a minimum, that I have what I have, all I'm going to do, I have x, I just want to get y. So y is equal to x minus 100. Y is equal to 50 minus 100. Y is equal to negative 50. So my two numbers are x is equal to 50 and y is equal to negative 50. Their difference is going to be 100, right? Check. 50 minus negative 50 is 100. And their product is a minimum. Their product is negative 2,500. So everything shakes out. That's my end result. Those are my answers. Okay, like I said, you have a couple of them in your homework like this. Similar question kind of on your exam / on your review. It's kind of a nice one. This kind of a good one to kind of get your feet wet in terms of, like, there's no pictures, there's no anything, two numbers, like, make it happen. All right, so I want to go back and I want to go talk about the cylinder problem. It's kind of a longer one, but it's pretty common, and it's a good question. All right, so a cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. All right, so first things first, I know this is how the question was written. All right, if you need this information, I will tell this to you. Number one, 1 liter is 1,000 centimeters cubed. All right, so we're going to use 1,000 centimeters cubed because centimeters is a distance unit, it's a length unit, it's a measurement. 1 liter doesn't really help us all that much. And then a couple of other things that we should kind of have handy to do this problem. Once again, if you need this on your exam, I will give it to you, all right? But a couple of things you should be aware of. The volume of a cylinder is pi r squared h. That's what it is. That's the volume of a cylinder. And then the surface area of a cylinder, all right, surface area meaning I say perimeter very loosely, but how much all those two areas are. So it's the two areas of those circles, right? If you think about a cylinder, the two circles on top, 2 pi r squared, that counts for the two circles, plus 2 pi r h. And that 2 pi r h talks about the metal wraparound, all right, if you think about a soup can. So we're going to need all three of these little nuggets of information here to do this problem. And it says, find the dimensions that will minimize the cost of the metal to manufacture the can. Now, a little bit less obvious, but if we're minimizing making the can, right? If you're minimizing how much it's going to cost to make this can, that means you want to use the least amount of material, right? That's the idea. You want to minimize, if you're going to minimize the cost, you want to use the least amount of material. We want to minimize our surface area, all right? So minimizing the cost of making this, we're going to minimize the surface area, minimize the amount of material used, right? So this thing is what we're minimizing. This volume piece is going to be helpful, right? We've seen this already, right? The second equation is going to be kind of what we plug in here in order to solve this. So let me go to the next page. We'll talk about this. All right, so I know volume is equal to pi r squared h. And if this thing holds 1 liter is 1,000 centimeters cubed. So I can say volume is 1,000 equal to pi r squared h. We don't want to use 1 liter because liter isn't like a distance measurement. Centimeters is. So that's why we do that little conversion. If you need that, I'll either write it in centimeters cubed or I will give you the conversion that you need. All right. And then surface area, 2 pi r squared plus 2 pi rh. This is what I want to minimize. This is the equation I'm going to minimize. So what I want to do is rewrite this guy and plug in to the surface area so I can take this derivative, right? Very similar to what we did, just got a little bit more moving parts. So it's up to you, right? Choose your own adventure, but choose hopefully wisely. 1,000 is equal to pi r squared h. You could either solve for r squared or you could solve for h. You would get h equals something or r squared is equal to something. My recommendation is to solve for h, because we just have to plug in one spot. If I solve for r squared, that'll help me here, but it would be a little bit harder to work with here. So what I'm going to do so that I get surface area in one variable is I'm going to solve this guy for h, and I'm going to get h is equal to 1,000 over pi r squared. Using this to plug into the surface area so I only have one variable so I can take the derivative, right? That's what we want to do. If you think about it, we did this kind of like with related rates with that cone question you guys saw, like about like four, like I feel like we saw this like a million times, like 4 questions or 4 times we saw that cone question where you plugged in and rewrote it so you got one variable. It's the same idea, all right? And this actually might be a little bit, some of you might think that this is a little bit easier. So the only thing I'm using this volume for is to rewrite so I can plug into the surface area to minimize the surface area. Okay, so surface area. 2 pi r squared plus 2 pi r, and h, I'm going to call this 1,000 over pi r squared. All right, one variable. That is what we want, one variable, because otherwise we're taking derivatives with 2 variables and it's not going to be fun. All right, promise. So let's simplify where we can, because then we can take derivatives nicer. Like the more work you do on the front end, the less work you have to do on the back end, right? So here's like the good news, right? 2 times 1,000, that's easy, right? 2,000. Pi on top, pi on bottom. Those are going to cancel out. And then I have an r over an r squared. That's just going to be r. So really not too bad. I want to take this derivative, so I'm just going to rewrite this r on the bottom as r to the negative 1. 2 pi r squared plus 2,000 r to the negative 1. Plugging in h, simplifying down to make your life easy, and then just rewriting it with that negative exponent so I can take the derivative. Once we're in good shape, once you feel good about it, take the derivative, s prime of a. We're taking the derivative of the surface area because that's what we're minimizing. That's what we want to, that's the idea. We want to minimize the surface area, which is why we're taking this derivative. Now, 2 pi r squared. 2 pi is a constant. It hangs on, so keep the 2 pi. The derivative of r squared, 2r, plus 2,000 is a constant multiplier. It stays. The derivative of r to the negative 1, negative r to the negative 2. That looks a little messy, so let's just clean it up here in the next step. We have 4 pi r minus 2,000 over r squared. Okay, so this is what we're going to set equal to 0. We're going to get our critical values and like hope for the best, right? This is going to look a little nasty, but it'll be okay. All right, so 4 pi r is equal, minus 2,000, I got ahead of myself, over r squared is equal to 0. And I'm going to set this equal, I did set it equal to 0. So we're going to set this thing equal to 0, which is what we did. Now, how do we solve something like this? All right, what I like to do is I like to bring one thing over to the other side, and I'll show you why I like to do this. So I'm going to bring this 2,000 over to the other side. I like to do this because, number one, I'm going to hope to get rid of this fractional thing here because that's kind of a nightmare. Like, I don't want to deal with that. And then hopefully, like, other things are going to, like, cancel out. Like, things might kind of work out for us. So what I'm going to do is I'm going to multiply r squared on both sides. I'm going to have 4 pi r cubed on the left and just 2,000 on the right. Now I don't have any fractions. Now I don't have to deal with that. We can move on. I want r. Remember, everything else, 4 is a constant, pi is a constant, 2000 is a constant. R is my only variable. So r cubed is going to be 2000 over 4 pi. Yikes, right? Like, that's a nightmare. 2000 divided by 4 is 500. I know that doesn't make it a ton better, but it's a little bit better. R cubed is 500 over pi, which means r is equal to the cube root of 500 over pi. I couldn't tell you what that was off the top of my head. Let's take a look. Oops. Struggling here. Math. Cube root 500 divided by pi. About 5.42, okay? About 5.42. That'll be helpful when we set up our table. Now, this is our only critical number. This is the only one we get. So we just want to make sure that it is a minimum. We're minimizing the surface area. We're minimizing the amount of material used. So I just want to make sure that we do get a minimum here. Now, once again, you could technically say from negative infinity to positive infinity, but if you were to look at this problem in a textbook or in our textbook or in, like you would see a similar problem, you would see that your interval to test would start at 0, right? We would want to make sure that, like, we're not going to have a negative length or anything like that. So that's why a lot of times when you see a problem like this, like, for sure you could start it at 0, but we also know that even though you could start it at 0, you're not going to have a 0 of a radius, right? Or you wouldn't have a negative radius. Like, everything's going to be positive, right? Bigger than 0. So I'm going to keep that in mind. I'm going to set my interval from 0, and I'm going to use my exact value for r. I'm going to say 500 over pi in that cube root. And then I'm just going to say r to positive infinity, right? We're going to just get real big here. I say 0, though, because, like I said, you can't have negative distances. You can't have negative radius, right? When you're making something. Okay, so pick some test values. So we know what r is equal to, just about 5.42. I could pick 1 and I could pick 6, right? Once again, I don't care what that number is when I plug into the derivative. I just want to make sure that it's positive or negative. All right, so here we go. 1 into the derivative. 4 pi minus 2,000, all right? 4 pi minus 2,000 is going to be negative. Now, 4 pi times 6, so 24 pi, minus 2,000 over 36, right? If you needed to double check your math on that, that will be positive. Okay, but you would get a positive number there. 2,000 divided by 36 is 55, and 24 pi, 75. So we're going to get a positive number there. What this is telling me, though, like I said, I don't care what the number is. I just know that at this location, I'm getting that minimum. All right, that's what I want. All right, so that's great. I get my min. Awesome. I know that r is equal to this cube root of 500 over pi. So the only thing left to do is determine what h is, right? If you're talking about the cylinder, you want the dimensions of the cylinder, you want the radius, and you want the height. All right, so height. If you're like, oh, this is not good, like, it's not going to look great. So 1,000 from h, 1,000 over pi r squared. So 1,000 over pi, and r squared, cube root of 500 over pi squared. Yikes, right? I'll give you what that actual value is in a second here. Let me do the math, right? So this is what we get for h times pi, 1,000 divided by that. we just get about 10.84. And these are in centimeters. The numbers aren't great, right? Sometimes that happens, right? I can only do so much about it, right? So the numbers aren't great, but that's how we do that problem. And it's a pretty standard max and min problem. It's definitely one, like I said, if you were to take calculus anywhere else, or like you saw it in a previous calculus course, this is a pretty common question. And if you are taking like a business calculus course, or any of that nature, like this is stuff that people care about. Like we care about maximizing and minimizing, and that's an important aspect of kind of like what we do, right, in terms of business and business models, etc. So this is what we've got.